So this is the divide. This is the Ogallala Aquifer. Old water, 10,000, 15,000, 20,000 years old, from the previous ice age's runoff from melting. Does somebody have a question about something? Okay. Funny story about the Ogallala. The rest of the world got sad because we got so hooked up with that much water. You may notice Nebraska is almost entirely on top of the Ogallala Aquifer. So Nebraska has lots of groundwater supply. So Nebraska gets to be the corn state. Kansas is known for making some corn. Easy for them with all that extra water. Oklahoma and Texas both have a little bit of agriculture around those sections. But here's the sad part. Everywhere you see that orange color, the Ogallala Aquifer has been overdrafted about 20 to 1, meaning 20 units of extraction for every 1 unit of recharge. The Ogallala Aquifer is running out. The water table is sinking. In some places, it's more than 50 feet deeper. You can imagine, if Ian has a farm, he's going to suck out water. All of a sudden, Jose City runs out of groundwater. I got to write all of you a letter that says, sorry, citizens of Jose City, by next year, you'll be responsible for your own water supply. We're shutting down water. You can imagine what that would do to your real estate. And this is a classic tragedy of the commons. Since I can't figure out who's taking all the water, the only smart thing for me to do is take all the water before it runs out, right? So it's a famous example of the tragedy of the commons. We've overdrafted by 20 to 1. The largest aquifer on Earth, the most voluminous supply of groundwater anywhere on the planet. And it's leading to collapsing agricultural communities and a lot of rural towns running out of municipal water. Kind of bad news. Okay. On number 16, two quick things for me to point out. Number one, desal is energy intensive. It's often said you're turning oil into water because you need the fossil fuels to make the electricity that's required to do the desalination. Turning oil into water. Very few people can afford the energy. So even though the technology is like 30 or 40 years figured out, we haven't figured out the energy for that technology yet. Yes?
Can they just do it through like distillation? Or like, how do they do it?
Yeah, but, how do they do it? Reverse osmosis. It's like a forced RODI. Reverse osmosis deionization. I don't think this diagram helps anyone. I don't know why it's in there. But this picture does show something that I want all of you to see. That's a desal plant. And the desal plant includes a power plant. In order to make the electricity, in order to do the desalination, they need electricity, and they need so much electricity that it's cheaper to make their own than it is to purchase electricity. So they are literally purchasing fossil fuels and selling fresh water. But the real future of this will be when we can make the fresh water without that much energy. Nanotechnology, the engineering craze of the moment, the way that your big brother and big sister are looking to get a job when they get out of college, is nanotechnology. This promises a new generation of desalination. More energy efficient. For those of you that want to get a 5 on the AP test, you might want to know these these names. Forward osmosis, carbon nanotubes, and biomimetics, or biomimetic membranes. These systems are either passive or very low energy. So once you get them built, they don't require a lot of energy. And we hope that within 5 to 20 years, we'll be able to really address the global water issue using methods like this. Yeah, probably 5 to 20 years, I would say. Do you guys realize that roughly 1 in 3 humans does not have reliable access to clean drinking water? And about half of humanity has to walk more than 1 mile to get their drinking water. Think about it, solving the water thing, that's probably the first major resource obstacle for our species right now. That's the biggest resource obstacle. Okay. Next, I'd like to talk about number 18, about water uses. Something you might notice immediately when you look at this diagram. Human population in the United States keeps going up. I'm sure you all knew that. And ever since the 1980s, total water withdrawn has been going down. So one interesting trend in the United States is that even though our population grows, our total water use is starting now to go down. Water use grew with population until the 80s, when water use per person started to dip. But when you break up the withdrawal into the different uses of water, I think that's where things start to get really interesting. I don't know if you can all see from back there. I'll try to read you the color coding. Those 5 columns are the 5 uses of water. From left to right, they are purple for public supply, green for rural supply, brown for irrigation, blue for thermoelectric, and a barely different from the brown with a teeny bit of red, the reddish brown at the end, that's industrial water use. First, the obvious stuff. If you look at public supply and rural, they've gone up always. Because population has gone up over that same period, that kind of makes sense. An interesting story is the industrial uses of water. If you compare the red column in 1970 to the red column in 1995, American industry uses a lot less water. There's 2 reasons. I forgot to mention in my other periods that a lot of our industry has been shipped overseas, where resources are cheaper, like water. So resource-intensive production has often been outsourced in the U.S. But second of all, through legislation and through competition, our businesses use less and less water. Industrial water use in the United States has decreased very dramatically since the 70s. it makes sense to use less because you have to spend less on that material, so you get more profit. Plus, it's become more difficult for industry to be wasteful with water. The real details, though, what are those two big stripes in each here? The two tall columns? Irrigation as in agriculture, and thermoelectric as in what? They're not for dams, that's hydroelectric, and that water is not counted as withdrawn. It's returned to the river. Exactly, the stuff we boil to make the steam, or the water we use to cool down the machinery. That's a lot of water. Now, you've heard me talk about efficiency as an economic thing. You've heard me talk about efficiency as a way to make our fossil fuels last longer. In a little while, the next unit, you'll hear me talk about efficiency as a way to protect air quality and human health and prevent climate change. But here's another reason to be more energy efficient. We have more water left over. I have to say, I kind of hate it when the commercial on TV tells you to turn off the water when you brush your teeth. Like, all things considered, that's like the least water of anything in your day. And you're supposed to focus on that one. They could say, don't wash your car. It's better for the paint anyway. Or they can say, turn off the light. That would really save a lot of water. Agriculture and electricity, when you put them together, add up to more than 90% of America's freshwater usage. That's a lot. That would be easy savings.
Do you know what percentages, like, actually use for drinking water? 0 to 3 or something?
I'm sure it's utter chump change. By the way, all the rest of that is drinking water quality. Almost all the water we use in the United States is potable. Most industrial waste water is made from drinking water. Like, we flush our poo with drinking water. Number 19, about how to conserve water. I'll warn you right now, is a big deal, and I'm not going to go over it in class. But I'd like to talk about number 20 very quickly, how to use groundwater sustainably, because in Santa Barbara, we do. The secret for groundwater is to put water into the ground and only take it out when it's your last resort. In Santa Barbara, we use wells when everything else has failed. The rest of the time, we use surface water. If we have to, we can get water from the Sierras because we are the end of the state water project. One of the things that we do in this city, we recycle our wastewater. How does that give you more drinking water if nobody drinks it?
Because you're using the stuff that you can't drink for other uses, and you can use the stuff that you would otherwise use.
That's right. We save the good water for drinking because we can water the school with wastewater. So recycling the wastewater, even if you don't drink it, gives you more drinking water. Because you can conserve the drinking water for drinking and use the wastewater for other purposes. So we recycle wastewater. We are connected to the state water project. We recharge groundwater on purpose. Look at this thing. Santa Barbara has the Twitchell Reservoir, which is a giant underground aquifer that we intentionally flood with runoff in the Cuyaba Valley so that we can stash any extra surface water underground, just as like a backup for the backup for the backup. We've got wells, we've got reservoirs,